Hello pre-calculus folks, this is Mr. McAllen and today I'm giving you the lesson on the mathematics of finance. This is from our textbook, section 3.6, and in this video we're going to be going over the items under the first set of objectives. We're going to talk about compounding interest, we're going to talk about compounding once per year, talk about compounding multiple times per year, and compounding continuously. So the example problems will be very similar to each other with minor changes to them, and the basic changes we'll be making is the compounding schedule. So just to get started, compounding is the amount of times that your savings account or your investment awards you interest for keeping your money in that account for that period of time. Interest can be compounded once per year, it can be compounded twice per year, quarterly, which would be 4 times a year. Any compounding schedule the bank would arrange with you can typically be done, and this is the formula that they use to do it. So the formula for it is, let's just write that out. It would be the amount of money as a function of time is equal to the principal that you start with, that's the initial amount you invest. It'd be 1 plus the interest rate changed to a decimal from a percentage over n for the number of compounding cycles per year raised to the n times t, and that would be in the power position. So this falls under the umbrella of an exponential equation because the variable of the amount equation is in the exponent position on the in the function. So with that being said, when we have one interest problem, like our first example, Robert has $500 to invest. He invested at 4% interest compounded annually. Now annually means just once a year, so that information would be n equals 1. How much money would Robert have if he invested it for 10 years? So we'd fill in the blanks on the equation. The amount as a function of 10 years is equal to, we're going to put 500 in for the principal, which is the initial amount, 1 plus the interest rate is changed to 0.04 over 1 raised to the 1 for n, 10 for the power. So we're going to simplify this before we start punching buttons on the calculator out. 500 times 1.04 raised to the 10th power. Now I'm going to go to my calculator because I don't know how to raise 1.04 to the 10th power. I don't want to do that type of math. So I'm going to just type in 500, put parentheses, 1.04, use the exponent caret button and put in 10 there. And when I hit enter, it's going to give me $740.12. So your interest would be, I'm just going to put this away, $740.12. So that would be the amount at 10 years. So what happens if we compound? Everything remains the same, but what happens if we now compound more than once per year? Let's just say, for example, twice per year. So again, the amount equation equals the 500, the principal, 1 plus the 0.04 for the interest rate. Here, I'll just write out the equation again. Amount as a function of time is equal to the principal times 1 plus r over n to the nt power. And now I'm going to be dividing by 2 because the number of compounding periods is twice. So I'm essentially cutting the interest rate in half, but I'm raising it to a power that is twice as great because n would be 2 and the number of years would be 10. So it's kind of like that's a compensating factor, but they don't compensate identically. So what's going to happen is we should end up with more money at 10 years. Let me just erase this t and put 10 in. So the amount at year 10 is going to be 500. This will be 1.02 raised to the 20th power. So let me go back to the calculator and make that adjustment. So I'm just going to go back up to the original equation and I'm going to change the exponent to 20, and I've got to change the number on the inside of the base to be 1.02. So then when I hit and when I hit enter, that I'm going to get $742.97. So that'll be $742.97. And I do make slightly more money over the 10 years. And, so that still represents a gain as opposed to just compounding once per year. So now let's look and see what happens if we compound. If we keep compounding and keep compounding more and more, do we keep making more money? How much more money do we make? So in this case, we have 4% interest again. Now we're going monthly, so that would mean that n is now 12. So the amount at time t, again, I'll write the equation. Now you're expected to remember this equation. So I'm going to put in the amount at year 10 again. I'm going to have 500. 1 plus, this will be 0.04, but now divided by 12. Raised to the power 12 times 10. So now we're going to compound interest 120 times, but we're going to do it with an interest rate that's 12 times less. So I'm just going to go back to the calculator and put that in all in one step, because I don't feel like calculating out the intermediate steps. So I'll have 500. I'll use parentheses. 1 plus, remember you have the fraction button on your calculator. You want to put in 0.04. Hit the down arrow for put 12 underneath. Make sure you close the parenthesis and we raise it to the 120th power. Now when I hit enter, it's going to show me I have $745.42. $745.42. So I have yet more money for leaving my money in the same interest. So I have about like $2.50 more. Not quite. I have like slightly, almost $2 more. But over 10 years, it seems insignificant. Let's see what happens if we compound continuously. Now, when you see the words compound continuously, it's time to switch equations, because continuous compounding would imply that the n value, n is going to infinity. But instead of using this formula and driving n to infinity, we use the PERT equation, which is principal times the exponential function, the natural exponent function, to the RT. Now, R is still the interest rate. We use this equation whenever we're told to compound continuously or we have a continuous growth model. So in this case, the amount at time 10 would equal our 500 we start with. We're going to use the e for our base, and that's going to be raised to the 0.04 times 10. Okay, so now on the calculator, we're going to do 500. Slight change in the equation because, again, we're using the exponential function. So this is going to be, let me just delete that. I'll put down, I have to do shift natural log so I get e. And this is going to be to the 0.04 times 10. And that should give me my amount as if the money were compounded continuously. And this would be the limit to what type of money I could make, because I can't compound any more than continuous compounding, and that would be $745.91. So the amount at 10 years would equal $745. Let me just look at that number again, and 91 cents. So that is a variety of problems that we would use. Remember the difference between the amount equation when we have continuous compounding and the amount equation for when we have discrete compounding. Okay, so the other type of problem that you might encounter is what happens if you are trying to figure out how long it would take for your money to double. This is just a different blank is being left empty in the equation, and we're expected to find what that time frame would be at 4%. So let's figure that out. So we fill in all the blanks. The amount of time t is equal to 500, 1 plus an interest rate of 4%. It's compounded annually, so it's divided by 1 to the 1 times how long would it take for your money to double. So we're actually solving for t. So if we're looking for the amount of doubling time, I changed the amount to 1,000 because my initial amount was 500. So here we have an exponential equation where we're trying to solve for the variable in the exponent spot. So what we're going to do is we're going to solve for that. We have 1.04 to the t power. I'm going to work on, I want to get rid of this 500, so I'm dividing both sides by 500. So I'm going to be left with 1,000 divided by 500 is 2. So now in order to solve this exponential equation, we would use any type of logarithm that you like. I always seem to like using natural log. So we say the natural log of 2 is equal to the natural log of 1.04 to the t power. That property of logarithms brings the t down in front of the natural log of 1.04. That equals the natural log of 2. And now I just solve for t. So t will equal the natural log of 2 divided by the natural log of 1.04. And when I do that on the calculator, the natural log of 2, close the parenthesis, divided by the natural log of 1.04, we'll find out that the time frame needed for the money to double at 4% would be 17, and let's say 17 2/3 years. So the t would equal 17.67 years. So basically, that would be 17 2/3 years. Now here's one other twist that this problem has. One other twist would be, suppose that you're looking for an interest. You get, let's say that Robert has 500 to invest, and he's looking for an interest rate so he can force doubling to happen in 10 years. In this case, he's trying to find that right type of investment. So again, he would write 1,000. Or well, let's write the original equation. The amount as a function of t is equal to the principal 1 plus the rate over n to the nt. He's going to be investing, it didn't say, oh, it said compounded annually, so we're just going to leave n to be 1. So the amount would have to become 1,000 to double. That equals 500. 1 plus the rate we're looking for over 1, so because it's compounded annually. To the 1 times t. So we know t is going to be equal to 10. So what we're looking for is, when we do the math, we're trying to solve for r. So what we do is we divide. And now because we have, we're trying to solve it for that r value, we're going to use the logarithms again. I'm going to natural log both sides. And that power 10 is going to come down in front. And I'm going to get ln of 2. I'm going to divide by 10. So I have ln of 1 plus r equals ln of 2 over 10. Now what I'm going to do is I'm going to use my calculator to compute that number. ln of 2 divided by 10, that's going to equal 0.0693. That's going to equal the natural log of 1 plus r. Now to get rid of natural log, I'm going to use the exponential function. I've got to use the inverse on both sides, so e to the 0.0693 equals e to the natural log of 1 plus r. And what I'm going to be left with is 1 plus r equals whatever e to the 0.0693 is, so let's see what that is. So shift natural log e to the 0.0693 gives me 1.0717. So that tells me that I have 1.0717. So when I subtract 1 from that, I'm going to get 0.0717. That would tell me what my interest percent is going to be 7.17%. So in order to double my money in 10 years, I need to at least be getting 7.17% 2% interest to do that. I hope this video has helped you understand some of the basics of finance with the compound interest formula and continuous compounding. There are a series of problems that I'm going to be citing in class, and I hope they, you should have the solution manuals or the solutions online to check your answers against what you do in class. Good luck.